All right, so your programming test 2 will be on Thursday during the lecture time. I'll see you there in the other way of the street, Williams Small Center. Your assignment number 4, that'll be the final programming assignment. I'm going to release it after the programming test for everybody. You can also tackle that. It's going to be also very good for your learning about the trees. And everything else is really something you know already about programming test 2, information, assignment 3, written test, whatever, right? So, and everything else the same, really. Yeah, nothing else to add. Any questions about the course? So the plan will be, we got only one lecture this week today, and then I'll confirm about the makeup lecture for your programming test 2 sometime next week. And then next week, we got 2 more lectures to cover a little bit about balanced binary search tree and maybe touch a bit about heap. That's something we'll do. We'll see how far we can go. And let's now take a look at some recap very quickly. And then move on to some new topic today. So last time we finished the last bit about merge sort, which is the running time. We basically say given a piece of Java code, you try to see the corresponding recurrence relation depending on the input sizes. And then from there, we try to solve it using an unfolding or winding, right? That's something I would expect you guys to do in the exam. Okay, I might give you something similar or maybe give you something a little bit different from what you see, but the principle is really the same. Got to make sure you how to go from the code into recurrence relation, and then given the recurrence relation, how do you solve it by identifying the patterns and see how you can reach out to the base cases. Right, take a look. Let me know if you got any trouble understanding it. Pretty basic. And in 3101, the sequel to this course, you're definitely going to learn about more general solution to the recurrence relation. That'll be for later. But for this course, I think it's a nice way to touch upon recurrence relation to appreciate its structure there. And we talk about the quick sort, and you can review the steps, but the most critical step is about choosing the pivot. As long as the pivot is very close to the median value, you're guaranteed to have an n log n running time eventually. That will be the best case running time. However, if your data is somehow skewed, and then the value you choose as pivot is actually very far away from the median. In that way, you might just end up having a linear time, like an n square, quadratic time, running time for the quick sort. So you got to be very careful about the quick sort. But arguably, quick sort might be a little bit easier to implement compared with the merge sort because concatenation, very basic. And also to choose a pivot, you just got to have some consistent strategy. So that's why people also use quick sort quite often in practice. But you got to be very aware about the pivot selection, right? That's the most important thing to keep in mind. All right, we spoke about the Java code, and you can also take a look at them on the lecture site. And we talk about tracing it. And then the worst case will be quadratic. You guys can also take a look at the recurrence relation. By the way, that's something I didn't quite mention explicitly. When you look at the recurrence relation, so let's say we are given some input of size n. And why is this one n minus 1? N minus 1 here is really the worst case you can run into for quick sort. That means apart from the pivot you have chosen, everything else will just go to 1/2. Right? That's really where the n minus 1 comes from. So think about the minus 1 here is to say, I just get rid of the pivot. Everything else will just go to the other half, which is pretty bad. You really want to halve them, like a left half and right half to be more balanced. Right? If you look at the best case, you can see that's exactly n divided by 2. Right? That's when you choose a pivot that's very close to the median. So really get into this kind of insight into the recurrence relation. They do tell you something very insightful about the sorting. All right, any question about merge sort, quick sort in general? All right, so now we have learned about 4 sorting algorithms for this course. We learned about selection sort, insertion sort, quadratic. We learned about merge sort, n log n, guaranteed. And we learned about quick sort, which can be as bad as quadratic or can be as good as n log n. Right, so these are the 4. And the final sorting algorithm, which I'm going to learn, either hopefully in-person lecture or maybe something you have to do in the makeup lecture, which is also very good quality. We're going to learn about heap sort. And to really learn about heap sort, we had to understand about binary search tree, first of all. And then we're going to learn about what does it really mean for a binary search tree to be balanced. From there, we can learn about heap, which is another kind of tree structure, right? Everything else you will follow. But heap sort will be the last sorting algorithm you will learn by the end of this course, of course, before you write the exam. Our exam is actually quite late in the exam period. It could be your advantage. It'll be April 20th. I'll reach out to you guys about if you feel like a review session. We can do it over Zoom. We can do it even 2 times You can ask me questions. I'll try to host an office hour during the exam period. Come talk to me if you want to. Right? All right. If no further question about merge sort, quick sort, let's now start a new topic today, which will be binary search tree. The slides is already on the lecture slide. I also did some last minute improvement for the iPad notes. You can take a look as well. Okay. So we'll go over the basic today. We'll see how far we can go, but I want to go very slowly about insight into binary search tree. That's really important, right? And then once we talk about balanced binary search tree, you appreciate the property even more. So we got, okay, so we're going to learn about binary search tree. So we already learned pretty well about binary trees. Okay, that's something very good. And recall to yourself right away, given n nodes in the binary tree, what's the lower bound and upper bounds for its heights? That's something you study for written test number, or just written test, right? Keep that to yourself. And we might reach there either today or maybe in the beginning of next Tuesday. And what we're going to focus on today will be something called search property. It's a very simple mathematical property that has to be checked recursively. If you want to check something recursively on a tree, that means you have to make sure that property holds on the root of every subtree in your tree. Remember, we'll talk about subtree is really the most important idea for you to run recursive algorithm on a tree. So search property is something we're going to focus on today. I'll give you different insights into the search property. And we're going to see a little bit about how you can implement binary search tree in Java. It just requires a little bit of specialization about your tree node class. A little bit different from what you're going to see in programming test 2. So just another kind of a case study, right? I'm going to show to you. Very similar. And for today, we might just be able to cover a little bit about searching through the binary search tree. And that is kind of straightforward. And then insertion is a very natural extension to searching, which we most likely have to cover next Tuesday, and also deletion. Deletion will be arguably the most complicated operation. There are about 3 or 4 cases you got to consider carefully. So we'll do that maybe next Tuesday. Okay? For today, just the basic fundamental property about BST. All right, so now let's define what a binary search tree is. First of all, it's a binary tree, which I don't need to remind you about its definition. Let's say, given a binary tree, how do we know it satisfies the search property? Let's go over the textual definition, and then we'll dive into some ideas. So this is the definition. Okay? We consider every internal node, meaning that the node having at least one child. And we'll call it P, okay? Just for now, parents. And we talk about the idea about an entry. So this entry here is also going to be useful when we talk about priority queue, which would be the heap lecture. Entry is like you got a pair of values to be stored. One is called the key, the other one is called a value. And key is usually for searching purpose. And the value is not really for searching. So you may contain some duplicates of the value, but for the key, you don't have any duplicates. Right? I'll mention a little bit more. But it's an entry, like a pair. And here's a search property. For every node in the left subtree for the parents, the value for their keys must be strictly less. And symmetrically, every node in the right subtree, their key value should be strictly larger than P. That's the textual definition. And just don't forget, this property here does not apply just to the absolute root on the top of your tree. It has to be applicable to every node of your tree, which can be the root of some subtree. That's something you want to keep in mind. It's a recursive property. Okay? Let's now try to visualize this property here. Right? That's a fundamental thing about binary search tree. Let me just go over this abstract definition again. Maybe just visualize it a little bit, and then we'll talk about why this particular tree is a binary search tree. We're going to talk about it. Okay? Let's start with the root. The root over here, for you to define the search property, let's call it P. Okay? So this one here, I'll just say that's P. Parents. And of course, P has left subtree, and also P has right subtree, right? Let's identify them right away, right here. So you can see this one here, the whole subtree here, rooted at the left child. That one there is a left subtree. Left subtree. And then we have the right-hand side, which is a subtree rooted at the right child of P. And that one there is the right subtree. Right? That's something you know pretty well. And let's talk about the entry. the P node over here stores, rather than a single value, think about it stores two values. It's something called an entry. And diagrammatically, we can just say it's a pair. Okay? So we say it's going to store two things. So it's going to store the key of P, and also it will store the value of P. That was key and value. Of course, in Java, you can say p.key and p.value. You can declare them as attributes if you wish. Or you can create another class called entry and then store key and value there. It's kind of up to your implementation. And it is very important to know for the key over here, it is for searching purpose. And the direct consequence of that is there should be no duplicates of keys in the whole tree. Otherwise, you got ambiguity, like which one should be matching the one you're looking for. So whenever you want to do any searching on the binary search tree, you have to give some key value. You don't search by the item value, typically, right? No duplicates. On the other hand, if you look at the value part for the entry, so this one here is actually just data value, which may contain duplicates, which is totally fine. Data value may contain duplicates. And for our discussion for searching, insertion, and deletion, we only talk about key value. So when you look at, for example, this particular tree here, so when we look at this node, we're just saying that it stores an entry, but we just omit the detail about the data value we're storing. It's not important. For searching, we can just focus on the key value, right? Just something you want to keep in mind, right? So the value here is just about the key. But in the reality, in the runtime, you really have key and also the data as an entry, right? But I'll get to the tree in just a moment. And then we say that every node in the left subtree must have their key value strictly less than the key value of P. So let me put a strictly less than symbol here. And then let's keep another greater than symbol over here, right? That's how you can understand conceptually. Question?
Yes, how do we assign the keys?
How do you assign the key? So in the BST tree class, I'm going to show you, whenever you want to create a new node in binary search tree, you got to assign the key value there in the constructor. That's how you assign it. In some occasion, you may want to, let's say, reassign the value of key by using some mutator. You might do that too. Yeah. When you first create a tree node in a binary search tree, you will actually have to initialize the key value. That's for sure. All right. Let's now get very formal, right? You guys learned about universal quantification. Let's use that to precisely talk about the property for search. Okay. How do we say the search property on the left-hand side? Okay, we say for every node, n is a node. And then we say n is a member of the whole left subtree of P. And if it is the case, then we say that the key of n should be strictly less than the key of P. Right, so this less than symbol here is really important, right? Strictly less. Let's see some example right away. If you look at this particular tree over here, right? Let's just look at one instance of the search property. You can see that the left subtree is right here. All right. If you look at that, every value over here is strictly less than 44. Okay. However, that one there alone is not sufficient to show that this is a binary search tree. You have to check this property here recursively, which I'll show you how you can check in just one moment. Okay. All right, so that's the left-hand side. Let's now do the right-hand side, which is very symmetric, right? So for the right subtree here, we're going to say for every node n is a member of the right subtree of P. And then, now you can imagine what the property should be, right? It's symmetric. Rather than less than, it should be larger than. So the key of n should be strictly larger than the key of P. Right? You can see here, we're talking about a larger than symbol. No equal. If you got equal, that means you allow duplicates, right? So like I said, key is for searching purpose, so duplicate should not be allowed. And for this one here, let's take a look. If you look at this right subtree right here, And you can now check very quickly. Oh, sorry, I could do better. There we go. All right. If you look at every node in the tree, you got 88, 65. Everything here is strictly larger than 44. Right? So the search property holds as far as this root node is concerned. Well, we got to check more. Question?
What I understood about BSTs, I thought it only applied to the immediate children of the root. As in, like, for example, take that node 54, right?
So you may be thinking more about the how you can implement the binary search tree property check, but I think conceptually you can think about every node in the subtree should be strictly less than.
Like, for example, if node 54 was like the number 3, for example, would that still be a valid BST?
Say it again?
If node 54 right there was like the number 3, for example, would that still be a valid BST?
54 there?
Like in the center, it's in the very center. Like
Yeah, want to change it to some value?
Like number 3, for example, it's less than that root node 44. Is that still a valid BST?
Are you saying that you want to change the value here from 54 into?
Like 3, like something less than 44.
Okay, this one, of course, it would not be binary search tree anymore because 3 here is not strictly larger than 44.
Okay, because I guess how I understood it, I thought that it was...
Could be a misunderstanding, right? Could be, yeah. But we can talk more, maybe after class. Okay. So what I'm talking about here using universal quantification is kind of visually how you can see it. But when you actually use a Java code to actually run the check, you'll do something a little bit more efficiently. That's something we can talk separately. Okay. So what your fellow student was suggesting is, said something you should do. We'll do some exercises. So let's say you're given some binary search tree. If I arbitrarily change the value of some node, you want to determine if it remains to be a binary search tree. Okay, that's something we'll do exercise as well. Okay. All right. So one more thing to say. So the search property should really 2 more things. Let's start with the first one. The search property should really hold recursively on the root of every subtree. The search property should hold recursively on the root of every subtree. Okay, so she hold recursively. For example, the one we just saw was as far as this subtree is concerned, right? It's the biggest subtree. And there's another one you should really check. You can check to see, let's say, as far as this particular root is concerned, it's a smaller subtree. In that way, I should really check to see whether every node in the left subtree has the key value less than 17. Indeed, there's only one node over there. On the other hand, if I look at this right subtree over here, you can see every value here, 32, 28, 21, 29, they are strictly larger than 17. So search property also holds on this particular root. Imagine that you got to check this search property on every root of the subtree, right? That's something you can imagine, right? I want to show to you. And of course, let's say for this one here, is this a binary search tree? By definition, it would be. But that's something we got to justify, right? So this is kind of the smallest binary search tree you can have with a singleton node that's internal, right? So that's something I want to talk about. So one exercise you should do is as follows before I talk about this kind of, I call singleton binary search tree. So what you want to do is I show you two instances of checking the search property. As far as this root is concerned, we did it. As far as this root is concerned, we also did it. And now what about for this particular root? Does it satisfy the search property? You want to convince yourself it does. All right. Also, what about for this particular root? Does it satisfy the search property? It also does. Right? You got to do this for every root of the subtree. Conceptually, that's something you want to start with as a beginner to the concept. But I'm going to show you very soon. There's another more efficient way to see in one go if this is a binary search tree. We'll get there. All right, let's talk about something here. It's a singleton binary search tree. Okay, let's now take a look at that. Okay, so what I'm saying is, let's say we have some internal nodes over here. So this is some internal nodes. And it has some value. Doesn't really matter. It could be x, key value. And then the way we show a singleton binary search tree is this. That one there has 2 children. And both of them are simply external. And for our coverage of this topic here, this is how we visualize the external nodes. Just square over here. So these 2 are just external nodes. External nodes. This is more like an implementation decision we're making for the coverage over here. What you could have done is you can say, I want to just set this one to be null and also this one to be null. That's another possible implementation decision, but we don't do that in the coverage over here. So I'm going to show to you the way these 2 external nodes are going to work is a little bit like a header and trailer that we talk about for doubly linked node. It's going to make your code structure simpler. Okay? So this one, these 2 are a little bit similar to the header and trailer in doubly linked node. That means it's only for your code structure to make it simpler, but they don't really improve the performance. Yeah, as we go over some Java code, either today or maybe next Tuesday, you will see a little bit more. Okay, but they are similar. Okay, which means at the runtime, so this will be an object, this will be an object, this will also be an object. We're going to have 3 objects here that's going to be set up. But I call this a singleton tree. We just got a single internal node over there. Okay, so why is this a binary search tree? Okay, so now I want to go back to our definition for the search property, and I want to show you something you may have seen before in 1090, but I don't really appreciate how practical that property is. Okay, let's now see. Let's now just go back with the definition. In order to satisfy the search property, what do we have? We basically have to say for every node over here, n will be, so we can say this is P, okay, parents. The left subtree of P. And then we have the key of n strictly less than the key of P. All right, we have that. That's something we saw just earlier. And also for every n will be the right subtree of P. And then the key will be strictly larger than the key of P. Right? So you can see one of them is larger than, and the other one is less than. Okay. Yeah, this symbol here, maybe you kind of learned it being a column or being a bullet point. Doesn't really matter, right? Both are acceptable. So now we want to know why this particular property here is going to satisfy this. Right? We're going to know. It's turned out to be very trivial. Do you guys remember something like this in the for the for all quantification? If I got for every and then x, and then if I say false, implies some property on x. What is that? Would that be true or false or something else? True. All right. It's something called a zero of implication. But let me make it more straightforward. Whenever you got some implication here, if the antecedent is known to be false, then it doesn't really matter what the consequence is. The whole thing, the whole implication is going to be true. All right? That's something you guys learned, but if you got trouble with it, you can let me know. This one here is called a zero of implication. And that is just going to be true trivially. And how can we actually apply this property here into the context over here? You can think about the external nodes over here, by definition, doesn't store any key value. So this will be the last node at the bottom over here. So that means you can think about the left subtree over here, it's just empty. And the right subtree here is also empty. Okay? So think about the left subtree over here. is basically empty. No nodes over there. No nodes that store any further key value for us to search further. And this one here is the right subtree. You can think about it. It's also like an empty tree, basically. No nodes for you to consider any further. So what I can do is I can replace this one here by empty. Replace this one here by empty. If I say n is a member of empty set, of course it's false. And n is a member of empty set also is false. So this part here is going to give me false. And also this part here is also going to give me false. So by this property here, it doesn't really matter what this property is already, right? It's just going to satisfy trivially because there's empty subtree, right? So as long as I got this value here, it doesn't matter because these two are just empty, right? So the whole thing is going to be equivalent to just true. So this one logically justifies why a singleton binary tree with just one internal node is a binary search tree. Okay? It's a subtle detail to really mention, but nicely connects to what you learned earlier in the logic course. Okay? In many cases where you want to prove some system property, this one here is actually quite handy for you to prove some simple cases or edge cases. Okay? All right, any question about this? All right, if no, let's now go a little bit further. Okay, this one's interesting. Okay, let's see. So we are done with this, the search property here, right? There's a diagram we went over. And also we talk about, okay, this diagram here, also I kind of mentioned earlier. So you can think about, let me just emphasize once more. Okay. If you look at the binary search tree here, these are just the internal nodes, which I color in green. They store some valid key value. Okay. These are the nodes where you want to consider their key value to see if they satisfy the search property. Or later, if you want to do any searching or deletion or insertion, you want to consider only those internal nodes with some key value. On the other hand, we also introduce like a sentinel nodes or guard nodes at the bottom. 1, 1, 1, 1, 1, 1, 1. So these are the external nodes, right? So that's really what the slide was meant to say. For our particular discussion here, we introduce these extra nodes, which wouldn't occupy that much space, just empty objects in some way. But they can make our code logic simpler. So we are trading kind of space for clarity of your code, which is valuable assets for you to have. Okay. All right, so that's some quick clarification. And let's now talk about sorting property. We talk about search property. Let's talk about sorting property. Sorting property in the sense that what's going to happen if you try to do an in-order traversal on a binary search tree? First of all, is it applicable for you to do in-order traversal on a binary search tree? What's the precondition for you to do in-order traversal? Should be a binary tree. Is binary search tree a binary tree? Of course it is. It's just a specialized kind of binary tree. So you can do in-order traversal for sure. Now we want to discuss exactly what's going to happen if you try to do in-order traversal on your binary search tree. That's something we're going to spend some time on. All right, let's now take a look. All right, I can give you the conclusion very soon, but we're going to really see how to build this up from scratch so you can appreciate why it will be the case. Okay? So let's now see here. So let's say given a tree that is a binary search tree. Given that it's a binary search tree, we know that the search property should be satisfied at every level, at every root of the subtree. Number one, we know that the search property is actually satisfied recursively. That's something we know for sure. And what about in-order traversal? Let's now recall very quickly what in-order traversal is about. And let's be a little bit more abstract. Okay? So let's now try to identify the three components for in-order traversal. Let's say this is the root. And then we got the left subtree. Oh, let's now use another one. Let's say we got the left subtree over here. And then we got the right subtree right here. Okay. And then let's say we got, so let's say this is a P, some parents, and let's say this is the left child, L, let's say left child, LC. All right, and this is basically right child, RC. And in-order traversal tells us we're going to do the following, right? We're going to do the in-order traversal. If I say I want to start with P, it's going to be broken down into three steps. Number one, I'm going to do recursively in-order traversal on the left child, on that left-hand side, which is guarantee whatever I come up with in that in-order traversal, all the elements should be strictly less than this. Right? Agree? And then followed by visiting P. And then followed by, I'm going to do in-order traversal recursively on the right child. And it's guaranteed whatever result I got in the sequence from the in-order traversal, every element there should be strictly larger than this. Does this sound a little bit familiar to you? We see some very similar pattern last Thursday in one of the sorting. Remember concatenation for quick sort? All right, if that kind of makes some sense to you, think about it. I'm going to write it down. You want to really think about what we're doing here for the in-order traversal for binary search tree, kind of compare that to the concatenation procedure for quick sort. All right. Okay, I'm going to write it down here. You want to really compare this one here, I would say a little bit similar to the concatenation of quicksort. Similar. All right. Okay, and then let's now do the in-order traversal. In-order traversal, we know that we're going to do left subtree followed by root followed by right subtree. And we know pretty well every element here has the key value less than the root. And every element in the right subtree has their key larger than. Right? Just a quick reminder. Right? The conclusion is, if you try to do in-order traversal of a binary search tree, you're going to get a sorted sequence. All right? For example, can you guys do something very quickly for me? Okay? Take this tree, do an in-order traversal. Take 30 seconds and verify that. All right. I kind of convinced at least a property holds, right, on this particular binary search tree. It's a sorted sequence. Okay, it's actually true in general, but I think we don't need to go for any formal proof. But I think let's get some intuition. Okay, so the in-order traversal, let's now build it from scratch. Okay, let me write down the in-order traversal first, and we want to somehow link between the binary search tree and the in-order traversal sequence. We want to see the correspondence. I think that's more important to see that. Okay, so let me write it down. So we got in-order traversal. So in-order traversal. So we got 8, 17, 21, 28, 29, 32, and 44. And then we got 54, 65, and then 76, 80, 82, 88, 93, 97. If I missed anything, please let me know. Okay. Now, how do we see the correspondence? Oh, before that, let me just say one more thing. So think about the tree structure over here is a hierarchical structure. It's nonlinear. Nonlinear hierarchical structure. On the other hand, the in-order traversal here is a linearized version. It's a linear structure. It's a sequence. All right, and now we're going to see how to understand the correspondence between the two. Okay. All right, let's see the correspondence. I would suggest we try to go bottom up in the following sense. Okay. So let's now try to look at all the singleton tree. Remember we spoke earlier, all the singleton trees should be a binary search tree automatically, right? Why don't we identify them first? So let me identify, let's say this one here, 8. Also, I got 21. I got 29. Also, I got 54. I got 80. And then I got 93. So these are the smallest binary search subtree we have in the binary search tree. All right. Let's see their corresponding parts in the sorted sequence. So we got A here. And then we got 21 here. And then we got 29 here. And we got 54 here. And then we got 80. And then we got 93. Okay, you can see the correspondence first, right? And then we try to look for some some bigger subtree that's going to reuse the already. Okay, for example, let's say for this particular subtree over here, right? That one there, we know the left subtree is already a binary search tree. The right subtree is also known to be a binary search tree. To reconstruct another bigger binary search tree, all we got to do is we join these two by a root whose key value is in between. All right, agree? Okay, so now let's look at this one here. So that one there, if you look at this one here, how do we see that correspondence? 21, 28, 29. If you look at just doing the in-order traversal for this one, 21, 28, 29 is sorted, right? So the way to see that would be 21, 28, and 29. So this is the subtree that we have over there. Itself is also a binary search tree. Okay, let's do a little bit more so you will get an idea. And what about this one here? This one here is interesting. That one there doesn't really have a left subtree, but it does have a right subtree that's known to be a binary search tree. To really make something that's bigger, that's also a binary search tree, you just join this one as a child right here. Okay, so we got 76 and 80 right here. So this is also something we have from there, right? Okay, let's go a little bit bigger. Let's go, just go right here, right? This one here corresponds to 93 and 97 right here. Okay, and then I think that's good. Let's now try to join something a little bit bigger here. What about this one here? If you look at this one here, right? That one doesn't have a right subtree, but its left subtree here, we argue, is already a binary search tree. So we can join them by left subtree, the root, and also right subtree. If you join that, it's still going to be a larger binary search tree. So that one there is going to be from 54, from 76 to 82. This one here, right here. Right? Can you get an idea, right? So we just got a few more. Let's make it complete. Okay. I can join another one. How about this one here? That one is going to include basically 32. And that one there corresponds to this part right here. You can see this. Think about what we're doing here. This part over here corresponds to this particular sequence. And when we join with another root, So every number here is strictly less than the root. And once we got the expanded sequence, it is still sorted. Right? So binary search tree goes very well with the in-order traversal when you see the correspondence in the sorted sequence. That's really the point I'm trying to make. Okay? Let's make it complete. What about this one here? This one here includes the 8 and 17. This is going to include everything over here. You can see the orange part over here is the in-order traversal of the left subtree right here. Okay? And let's do 2 more, and then we're done for this illustration. So what about I want to include the 65? All right, in the middle. So that means I'm going to get this one here to here. Okay? You can see that 65 corresponds to here. 54 is right here. And this subtree here is this sorted sequence over here. Right? A final one I want to do is this one here. Let's say I want to include 88. This one here. Right? That one there is going to include everything over here. So the green subtree here is going to contain basically this one here, which is this subtree. And the blue one here, which is this subtree. And then the root, 88, somewhere in between. And finally, if you try to join these two together with the 44, you're going to get sorted sequence still. That's why I really want to compare with the concatenation operation for quicksort. Okay, again, let me just emphasize that. Very similar to concatenation in quicksort. Any question? All right, it's a very important property here. That's why I really want to show to you how you can build it up from scratch to see the correspondence. Of course, you still want to know how to do in-order traversal separately, but to really see how the tree, each subtree corresponds to some subsequence in the in-order traversal outcome, that's really something you're supposed to know, right? You can see the insight. One more thing to say, and then we'll take a short break. So if you go back to this particular binary search tree over here, right? One way to check it is by check the search property for every root of the subtree. Now you know a more efficient way. What will be the more efficient way? If I give you a tree, I can ask you, is it a binary search tree? All you got to do is, why don't you do it in order traversal, and to see the sequence is sorted. If it is, it's a binary search tree. If it is not, it cannot be a binary search tree. That's a more efficient way to say that, okay, to check it. If there's a true or false question. All right, why don't we take a very short break by taking attendance. Okay, so before the break, we spoke about the sorting property. You can look at slide number 5, okay? So we don't really do any formal proof about this in-order traversal is going to result some sorted sequence from binary search tree. But if you look at the justification there, it should be enough for you to see some intuition there, right? We did things from scratch before the break. That's something you will be expected to study very carefully, and I might ask you some question about it. Not exactly sure what question, but maybe something. Okay. All right, so before I talk about Java code, I'd like to do 2 things to just to recap, and so also some exercise together with you. Okay, how about this one here? Oh, sorry, forgot to switch. There we go. Easy, okay? Well, of course, this is the more like a mental way to check. You know, if you got the diagram already, you can simply check to see whether every element, just check recursively. Or you can just do the in-order traversal, okay? So this tree here is already guaranteed to be a binary search tree because if you look at it in order traversal, it's sorted, right? So now here's my question. Let's say if I just modify one of the nodes. For example, if I change from 76 right here to 69. Is this still a binary search tree? Let's say yes or no question. Yes? Okay. Yes, I agree. And if you try to see a little bit more insight into this, what you're doing is you're basically impacting just one of the subtree. Try to look at the smallest impact you're trying to create. This one here is basically this particular subtree, right? That one there used to be 76 and 80. And you're basically just modifying from 76 into 69. This is okay because you are substituting the value over here by something that's still in between 65 and 80. It's a very important insight. All right? Okay, because 69 is in between the 65 and 80. And I'll speak a little bit more about it. We call this 80 here the more like a successor in the in-order traversal. And we call the 65 over here the predecessor, right here. One thing here that's very interesting. One thing you may want to study before next Tuesday when we talk about deletion, this will be very useful. If I only look at this node here, if I only look at the tree, if I only look at this node here, in the linear sequence 69, let me say it again. This one used to be 76, which is right here. The predecessor and successor in a linear structure is very easy to see, just before and after. However, in the original tree, it may not be so obvious. You want to say 76, the one that goes before that is actually 65 over here. The one that goes after that is actually 80. These are the things you want to watch out for when we do deletion. Right? I may not say too much about it, but you want to convince yourself. Okay? This is the predecessor of the 76 in order traversal. And this 80 over here is the successor of 76 in the in-order traversal. To really know where the predecessor and the successors are in the corresponding in-order sequence, in the in-order traversal sequence, is going to give you the justification when you do deletion, which we'll talk about next Tuesday. Okay? Just keep that in mind and think about it to yourself. Okay, one more. What if I try to replace, let's say, the 65 over here by 83? Is this still a binary search tree? Yes? No? No. All right. No, I agree. But again, let's see very quickly the correspondence. Okay. In the original subtree, which is right here, which is from 54 to 82. This is the original subtree. After you have done the in-order sequence, everything else will just be sorted, so you don't need to worry. We'll look at the smallest impacted area, really. The one we tried to change was from 65 into 83. Apparently, this is not good, because whereas this is still larger than the predecessor, that's okay, but it's no longer strictly less than the successor. That's the problem. Okay? Not acceptable because 83 strictly less than 76 is false. So it cannot be a binary search tree. So if there's any key change you want to introduce on the binary search tree, you got to make sure the resulting tree is still a binary search tree. That's the main learning outcome from here. Okay. And one more thing to say, let's say if you look at the predecessor, that'll be 54. If you look at the successor, it will be 76. Okay. So you want to look at this one is the predecessor of the original 65 in the in-order traversal. In-order traversal. And the 76 over here is the successor of 65 in the in-order traversal. Okay, we're just doing similar annotation here. Okay. And let me do one more summary, and then we can go on to see some Java code. Okay. Let's now try to do a more abstract summary right here. Okay. imagine that we have the general structure for a binary search tree. So let's say we're given some binary search tree. And it looks like this. So let's say we have the root, let's call it P again, the parent node. And then we got a left child and a right child. So we got some link over here and some link over here, left and right. And then we got left child and we got a right child over here. Okay, and then we have this one here. The tree rooted at left child is going to be the left subtree. And the tree rooted at the right child right here is a right subtree. Okay, so far we got 3 nodes. We got one here, and one here. All right, and let me introduce another 4 nodes. Let's say, for the sake of illustration, let's assume somehow these trees are relatively full, and we got similar heights for the 2 subtree. Let's say, okay. So let me identify another 4 nodes for you. Let's say I got one node right here. I got one node right here. And then I got another node here. And I got another node here. Okay. Let me call this one here N1. And this one here N2. This one here N3. And this one N4. If I try to do some in-order traversal, of course, there might be other nodes that might go in between these nodes, but I'm more interested in the order of these 1, 2, 3, 4, 5, 6, 7, these 7 nodes. What's going to be the sequence if I try to do in-order traversal? Anybody want to give it a try? If I do in-order traversal of this binary search tree, well, even just a binary tree.
So it would be N1 left child, N2 parent, N3 right child.
Yeah, that's pretty good. All right. So it's going to be something like this. It's going to be N1 followed by some stuff, and then you're going to get the left child followed by some stuff, and then you're going to get N2. And then followed by that, you're going to get P right away. Nothing in between. Okay, let me just make a little bit more space here. And after P, you're just going to get N3 right away. No stuff in between. And then you're going to get something. And you're going to get right child. And you're going to get some stuff. Okay, you know what? Let me, I want to put it in a new single line. Let me put it here, at the bottom here. Oops. Okay, let me organize that a little bit right here. There we go. Okay, after the right child, we're going to get some stuff. And then we get N4. Right, so we cover 1, 2, 3, 4, 5, 6, 7. 7 nodes, right? Convince yourself why this will be the case. You can feel free to create a binary search tree yourself to see why this order. Okay. Okay, let me highlight a few more things. These will be also useful when we talk about deletion. This one here, N1, apparently should be the minimum key. And also N4, the rightmost, should be the maximum key. It's very obvious to see that in the sorted sequence, but may not be so obvious in the tree. Now you see that, the correspondence, right? This will be the maximum. And I want to speak a little bit more. What about N2 and N3? Okay, N2 is right here, N3 is right here, relative to P. Right? If you look at let's say in the sorted sequence, it's quite obvious. But if you look at it in the tree, it's here followed by this, followed by that, right? Okay. How can we characterize N2 and N3? I'm going to write it down. This will take some time to digest. N2 is the largest key that is strictly smaller than the key of P. Because we know all the keys in the left subtree must be strictly less than P. However, N2 here is the largest among them. Symmetrically, all the key values in the right subtree must be strictly larger than P. But we know this guy here got to be the minimum. Because when you start in order traversal on this subtree, you got to start with that. Okay, think about these insights. It's really important. Right? The smallest key that is strictly larger than the key of P. The most important things we learned today is really to see how we connect between the hierarchical structure that's nonlinear into the sorted sequence that's linear. That's really the insight you want to digest before next Tuesday. Okay? Because when we talk about deletion, these insights will be very important for us to justify after deletion or insertion, we still get a binary search tree. Okay? All right, guys, any question? Okay. Okay. All right, so if you guys are okay, let's now talk a little bit about Java, right? Which is not too bad. It's very similar to how we define a in some ways, it's a better, an easier structure to work with compared with a general tree. For your upcoming programming test number 2, for the children, you have to work with the singly linked node, right? But for binary tree, since we know there's only left and right child, we don't necessarily have to use a singly linked node. We don't have to. We just use the left and the right. So that's simpler a little bit, okay? But let's now talk about it. All right, so that's example code. It's also on the lecture site. Also play with it. When you write the exam, you got to make sure you're familiar with both this version here and also the general tree version, right? So you should really know both, right? You got different implementation or design choices you got to get used to. It's a generic class. It's a generic class. You can see E here. And these are the attributes we have, okay, right here. And if you remember the concept about entry, we got a key here. And also we got a value here, right? So these two constitute entry. And of course, for search purpose, you only use a key, entry. And we got 3 pointers. We got parents, we got left and right. No singly linked though, as I explained, right? You don't need it. So we got parents, and then we got left and right, which I'll visualize with you in just one moment. Okay, we got left, we got right. Okay, and you got some different methods here. You can go over them. You got whether or not the node is external and whether or not it's internal. Very useful accessor method. You can take a look at the definition yourself, right? Just make sure you get familiar. And also we got other methods over here as well. Just a very conceivable methods for setting the key, setting the value, and getting the key, getting the value, and parent, getting the left, etc. Right? So these are very standard definition you can see. Okay, I'll leave them to you as well. We don't need to waste time in the lecture. I want to clarify, since we talk about the difference between internal and external, right? So let's say this is internal nodes, which has 2 children of the external node, for example. Let's say over here. So this constructor over here is for creating external nodes like this. That one there doesn't take any value for key, doesn't take any value. So that's going to leave the default value for key and value just null. Okay, that's how we create such a node. You will see that. Okay, and this one here is going to create some internal nodes with the key and value being not null, right? So that's for this one here. Okay, just notice it's overloaded. constructor. Okay. And let's visualize very quickly about the binary tree node structure. So we got, let's say, some node n. Okay, so that one has several attributes. First of all, we got parents. So the parent is going to, so parent link is going to point to somewhere up. And also we got the key and value. Also we got another two attributes over here. We also got the key, and also we got the value. You know, for example, key could be, let's say, 23, and the value could be maybe some string value, for example, Alan, right? And finally, we got another two attribute left and right, which will be pointing to another two binary tree node, BST node. All right, so this will be the left, and this will be the right. Okay. And let's revisit the idea about nonlinear versus linear once more. Okay. Remember the way we define nonlinear. That means either the predecessor or the successor is not unique, right? So you can think about in some way the parent link is unique. You can think about in this part here, it's a unique predecessor. But that one alone is not going to make the tree linear, of course, because you got violation here right away. So think about over here, you actually got the left and right here. So these two are, tells you got non-unique successor. You got more than one, right? So that's why the tree structure here for binary search tree is nonlinear. Right, which is revisiting the idea we spoke about earlier, right? Maybe around before the reading week. And something you can also do by yourself, you can try to visualize the doubly linked node where you got the previous, you got next. So that means you got unique predecessor and unique successor, right? So that's why it's a linear data structure. All right, any question? Yeah.
What's the motivation for like using key and value instead of just like element like value?
Okay, so the question was, what's really the motivation for using an entry? Why don't we just store a single value? So it's called a separation of concern. It's a very nice software engineering principle. We're handling two things. Let's look at here. So think about, let's say here. This is a node. Okay, let's say here. Okay, let's look at this tree here. So each node stores an entry. We got a key and also we got a value over here, right? So key is only for one concern, for searching. So we got to make sure key should be the value that you can fast compare, in which case we can just use integer. On the other hand, for the other part of the entry, you got some data value, which may not be an integer. It could be an object, could be a string, or could be some complex structure like maybe person, employee, or whatever structure you have. Those structures may not be so easy for you to use to search directly. So that's why we kind of separate these two concerns. One is for searching, the other one is for data storage. Yeah. Mm-hmm. That's something we'll cover a little bit more. It's something called like a dictionary data type, if we get a chance. Okay. All right. Let's now move on to take a little bit more about the code. Okay. So given this structure over here, let's take a look at how we can define in order traversal. Right. So this will be the precise code you can run. Right. So let's say here we are given the root of some tree, right? So let's visualize that right away, okay? So let's say we're given the root. The root is actually pointing to some node right here. And we can follow the left child and right child, right? So you can see we got a left link, we got a right link. So you can follow the left, and you can also follow the right. And each one of them is going to be some node. You can check to see whether they are null. If they are null, of course you're done. That's a kind of base case. If they are not null, you got to go further with the recursion. So this will be some node here, and this will be some node right here, right? In general. And this, of course, is going to be the left subtree. And this one here is going to be the right subtree. Oh, sorry. Right subtree. All right. And we try to store the in-order traversal into an array list, which you guys know pretty well. Okay. So return type here is just an array list of BST node. And then we are trying to, let's look at the different cases. We are saying that if the node we are given is actually internal, which means we are not really handling any case like this, in which case it's external, we don't need to go any further. We can just skip. Okay. So if it is internal, we're going to execute this block of code right here. Okay, right here. And the structure here is actually quite conceivable. We're basically saying go to the left and go to the right. If they happen to be internal, that means there's at least some node in the subtree, so we should really traverse further, right? If the left subtree does have some node over there, we're going to call the in-order traversal and get left. And symmetrically, we might go to the right if necessary. So it is really important to notice we're doing that conditionally. But of course, we might do both. And so the two recursive code we are making is right here. So this is the method here. And then we're making the first recursive call, and we're making the second recursive call. All right? Like that. Very easy code to understand. I'll encourage you, try the breakpoint, try the debugger, and then to see how that works. But let's see some example test case right away. Any questions so far? Yeah?
So this might not be particularly related to this, but with the question he was asking before with why we have an entry versus an element. Does that mean that we have to somehow be able to turn our element into the entry, like somehow convert it, like a transformation?
Not really. Just the way, okay, think it this way. The way you're gonna create the binary search tree, of course, you're gonna follow the definition for this class over here, right? So the only way you can create objects from this class, there are two ways. Either you pass no arguments over here, in which case the key and value will just be null. It's as if there's no entry being stored in the external nodes. On the other hand, this overloaded constructor here is going to create an internal nodes, in which case you're going to pass some key and value.
But if we want to compare, let's say, a string versus another string, and they are ordered, like let's say it's alphabetical, do we have to somehow create our own key?
Let's say, okay, sure. You're talking, okay, so the search property that we spoke about earlier, we say some integer strictly less than some integer, right? But if you really want to say alphabetical order, in that case, you would just have to make sure your key is a string type as opposed to integer type. Because when you say a string is less than another string, it's going to compare by default alphabetical order. It just in class for illustration, we use integer as a key. It's a very typical one. But if you really want to have another way to really do like a key comparison, you can do other object type if you wish. That's kind of beyond the scope for this course.
But then we assign the key, like we kind of relate the key and the value together. So like
Think about the key and value are kind of separate. Key over here is only for searching. That's for you to fast locate where the entry is in the tree. Once you locate the entry, let's say you get an entry back, you can say entry dot get value, something like that. Different purposes. Okay. And it's a good question here. For those of you who might be interested, again, it's outside the scope for this course. If you want to try anything other than key, so that can be for you to compare different keys for searching purpose, you can look into, there's a class in Java called comparable, I believe. Right? This class over here actually just is more like an interface. You just have to make sure you implement the method, but outside the scope. If you're interested in exploring, you can feel free to do that. Or we can speak about it. Good? All right. All right, let's now talk about some test case right here. Okay, this might be the last thing I can discuss today, which is okay. I can do searching, insertion, deletion, maybe next time. Okay. Let's do this one here. This one here is going to illustrate how we can construct a tree, and also we can do in-order traversal. Okay? Let's now do step by step. The step number one, we're actually going to create all the nodes right here. So we're going to create internal nodes, these are all the internal nodes. This, and these are the external. All right, you can see we're calling for external node just the empty argument version of the constructor. Whereas for these, I got integer key, I got some string value, right? You can see different constructor being called. Let's now try to visualize what's happening over here. So we're creating 3 internal nodes. Let me show you first, what kind of structure are we creating? Let's say we want to create something like, at the top, I want to have the key 28, and then that one there will store Alan. And I want to have a left child and right child for that one there. And then I got here, so let's say 21, and then Mark. And over here, I got 35 and Tom. Okay, Alan, Mark, and Tom. And let's say these two are the last internal nodes. So for external nodes, I can just write them as like that. Okay, that's conceptually what we're going to build. We're going to build 1, 2, 3, 4, 5, 6, 7 nodes. Okay, all these 3, you can see them right here. So I got 1 here. I got 1 here. I got 1 here. Okay, so these are the 3. And let's now fill out the information. So I got N28. Also I got N21. Also I got N35. All right, so these are the 3 nodes. And then the key here, 28, 21, 35. So 28, 21, and 35. And for value, Alan, Mark, and Tom. So you can think about Alan here, Mark here, and Tom here. Okay, so these are the 3 values. Okay, Alan, Mark, and Tom. And then, at the moment, the left and right just null. At the moment, okay, let's not bother drawing them. We're going to set the links in the next phase. And then we're going to create the external nodes. We got 4 of them. And the way to draw that would be just, we don't need to redraw the diagram, like the object diagram. We should just make it a little bit more conceptual. So I'm going to get 1 here. I'm going to get 4 of them. So 1, and then 2, and then 3, and then 4. Okay, these are the 4. And let's now put their references. External node 1, 2, 3, 4. External node 1. External node 2. External node 3. External node 4. All right. The final thing, may not be final, but let's see here. Let's see the next phase. We're going to set the references right here. Okay, what does it really mean when we say N28.setLeft, N21? N28.setLeft, N21. The left is going to point to here, right? Symmetrically, N21.setParents, N28. N21.setParents, N28. So this should be, the link should come back. Okay? And we do something very similar in the next few lines. Okay, I'm going to do it at one go, but you can definitely try to trace conceptually. Very easy to see. So this one here, the right is going to point to this node here, and the parent will point back symmetrically. And think about the left is going to point to here, the parent node will point back. The right will point to here, and parent will point back. Left point to here, point back. Right here, and point back. Okay? And if you look at the, we try to call the in order list traversal over here. That one there is basically going to do in order traversal this followed by that, followed by that. It's easy to see, of course. It's going to be 21, followed by 28, followed by 35. That's exactly what you will see right here. 21, 28, and 35. So that is the sorted in order sequence. All right, any question? All right, I think I'll pause over here, and then good luck to your test on Thursday, and then we're going to continue from this on Tuesday next week.